Greetings everyone, this is Mr. Muller, and in this podcast I'm going to wrap up the discussion I had in class on Friday. So I would like to talk about torque again. In class we talked about the fact that if I have a force that's not directed perpendicular to the door, it's directed at an angle, that it's only the perpendicular component of the force that actually helps to rotate. And that F sine theta was actually just going to be representing that perpendicular force. Well, another possibility exists, and that is one where I've got an object. This might be like an example of a door. It's kind of like already kind of tilted open, and I'm going to try to close the door, and I come in and I exert a force on it, and I'm trying to close that door. So as I'm trying to figure out, what the torque is going to be, I would find my axes, and I would draw a line going from the axes to where the force is applied, and that of course is my radial line. And then I would look at my force applied. Now I can really kind of think about this door as kind of being in this box. As I'm pushing on it, I'm just trying to think of all the dimensions that are going on here. So when I try to figure out what my torque is going to be, here is my little radius there, and there was my force applied. My radius was going down to here. Then what's actually causing the door to help close is not actually going to be all the radius that's going to be helping me. So when I look at my force pushing, some of that radius is going to be perpendicular to the push, and some of that radius is going to be parallel to the push, the radius away from that axis. So when I'm trying to find theta, which is the angle between the line of action and the radial line, and I'm looking at that angle there, that perpendicular side of the radius, that's the same side as up there, that's actually going to be the only part of the radius that's going to be responsible for the force. So R perpendicular times F. When I'm looking at that torque being applied, what I'm really concerned with is the amount of the radius that's going to be perpendicular to the force, just like I was in the last example. The only difference now is that the radius perpendicular is going to be the perpendicular piece, and then the force is going to be whatever it was applied. So when I look at my equation, RF sine theta, and I look and see R sine theta, if I look at my little triangle, that side that is representing R perpendicular is the opposite side of that triangle. That is just going to be my R times sine times theta. That's all that's going to be. And that's going to be multiplied by the force. This here is on your equation sheet. This one was not on equation sheet. So when I look at this here, I just want to kind of point out that it's only the perpendicular part of the radius that affects the torque. And we have a fancy name for R perpendicular. That's going to be the component of the radius that is perpendicular to the force acting, and that is known as a lever arm, or a moment arm. So that's the actual radius component that is actually helping you to torque that object. Okay. So I'm going to try to do an example problem using that last principle. This is example number 6. Example number 7 is in another video that I also posted. So when I look at this problem here, I've got this object that's going to be rotating. I apply a force at the corner of it, and here's my axes in the center, and I'm going to try to rotate this object. So the first thing I would do is I would draw a line from the axes to where the force is applied, and that's going to be my radial line. So that means this little distance here is going to be my R. Now that R, so there's my radial line. my line of action here is going to be the same direction as the force applied. So there's theta. If I wanted to use, I say, okay, I know torque as I look at my equation sheet, RF times sine of theta. And I look at my shape here, and we could actually probably go and find the angle if we wanted to, but it might be a little bit more time intensive. Let's see if there's another way we could solve the problem. So I remember that r sine theta, and I look at my equation sheet right next to it, that was just going to be the perpendicular component of the radius. That's all that represented. So if I know the lever arm, or r perpendicular, I can multiply that by that 200 newtons and go from there. So I look at this weird little shape, and notice that it's 46 centimeters long, which means to the axes is halfway, 0.23 meters. And when I look at what that 0.23 meters must represent, if my radius is that hypotenuse, and I look at my force here, then that distance must be the lever arm, the r perpendicular, that 0.23 meters. So I can multiply 0.23 times 200, and we're going to get 46 newtons times meters. Now, just like in the rest of physics, the direction that something was moving always mattered. The direction matters. So for here, if an object's rotation direction can be different, it also matters. So I'm going to add on here CW, which means clockwise. So I would need that direction for torque. I needed to include the direction. And by definition, counterclockwise is going to be positive, and clockwise is going to be negative. So I would also expect negative 46 newton meters, which implies that it's going clockwise. All right, that's the last piece I was going to put on this podcast. I hope this was helpful. Again, I apologize for the schedule. Let me know if you have any questions when you come back. Have a great weekend.